Welcome to this presentation on memory management in Linux. In this video, we will explore the essential techniques for monitoring and optimizing system memory usage in Linux environments. Let's begin by understanding the different types of memory in Linux. First, we have physical memory, also known as RAM or random access memory. This is the hardware that your system uses to store data temporarily. Next, we have swap space, which acts as virtual memory. It is a portion of the hard drive that is used when physical memory is full. Then there is shared memory, which allows multiple processes to access the same memory location. Following that, we have buffer and cache. These are used to improve system performance by storing frequently accessed data. Lastly, kernel memory is reserved for the operating system's core functions. Now let's look into some of the key memory management concepts in Linux. These include memory allocation, which is the process of assigning memory to processes. Page tables are used to map virtual addresses to physical addresses. Memory mapping involves mapping files or devices into memory. When the system runs out of available memory, the OM or out of memory killer steps in to terminate processes. Finally, memory overcommit is a technique where the kernel allows processes to allocate more memory than is physically available, relying on the assumption that they won't use it all. Now let's move on to some basic commands for monitoring memory usage in Linux. The first command is free. Typing free-h into the terminal will display the total amount of free and used physical and swap memory in the system, including buffers and caches used by the kernel. It presents this information in a human-readable format, such as kilobytes, megabytes, or gigabytes. The next command is top or top. These are interactive process viewers that show system resource usage, including memory consumption by each process, in real time. Top provides a more user-friendly interface compared to top. Let's take a closer look at the output of the free command. Running free-h provides a summary of memory usage. The total column shows the total installed memory in the system. The used column indicates the amount of memory currently in use by processes. The free column displays the unused memory that is available. The shared column represents memory shared by multiple processes. It is important to note the available column. This shows the memory that can be allocated to processes without causing the system to start using swap space, which can slow things down. Now let's talk about the buff/cache column. Buffers refers to memory used by kernel buffers, while cache includes the page cache and slabs. Linux uses free memory for disk caching to improve performance. This memory can be quickly reclaimed when applications need it. To see separate columns for buffers and cache, you can use the command free-w. It's worth knowing that high buff/cache usage is normal and actually beneficial for overall system performance, as it speeds up access to frequently used files. Let's explore some advanced tools for more detailed memory monitoring. The first is vmstat, which stands for Virtual Memory Statistics. By typing vmstat25, you can report information about processes, memory, paging, input-output, and central processing unit activity. In this example, the arguments specify an interval of 2 seconds and a count of 5, meaning it will update every 2 seconds for a total of 5 times. This tool is excellent for monitoring memory over time and detecting swapping activity. The second tool is the /proc/meminfo file. By typing cat/proc/meminfo, you can view detailed information about random access memory usage. This file contains dozens of memory-related metrics and is used by tools like free and top. To filter for specific memory information, such as swap details, you can use the command grep-iswap/proc/meminfo. Now let's look at monitoring memory usage for specific processes. You can use the ps command to display memory usage by individual processes. Typing ps-eopid, pid, cmd, %mem, %cpu double-sort equals -%mem piphead will show the process ID, parent process ID, command, percentage of memory used, and percentage of central processing unit used for the top processes sorted by memory usage. This command is useful for quickly identifying which processes are consuming the most memory. You can also use the pmap command to view the memory map of a process. By typing pmap-x parenthesis pitoff Firefox parenthesis, you can see a detailed memory map of the Firefox process. The resident set size indicates the actual memory being used, and dirty indicates the memory that needs to be written to disk. To get a total, you can use pmap-X parenthesis pitoff Firefox parenthesis pipegrep total. Use this command with specific process identification numbers to analyze memory usage patterns. Let's understand the different types of memory usage metrics. Virtual size, often abbreviated as VSZ, refers to the total virtual memory allocated to a process. This includes all memory that the process can access, but it may not all be actively used. Resident set size, commonly abbreviated as RSS, represents the actual physical memory used by a process. It excludes any memory that has been swapped out to disk, providing a more accurate representation of memory usage. Proportional set size, known as PSS, accounts for shared memory proportionally among processes. This is a better metric for applications that use shared memory across multiple processes. It is worth noting that resident set size is typically the most useful metric for monitoring real memory consumption. Finally, let's look at SMEM, which is an advanced memory reporting tool. After installing SMEM with sudo apt install SMEM, you can run smem-t-k to view memory usage. This command displays unique set size, which is the memory unique to a process, proportional set size, which is the shared memory divided proportionally among processes, and resident set size, which is the total physical memory used by each process. The SMEM tool provides more accurate memory usage reporting, especially for processes that use shared memory. Let's move on to swap management. We can monitor swap usage using the command swap-in-double-show. This command shows all active swap devices, displaying their size, usage, and priority. Also, you can use free -h pipegrep swap command to see the total swap space, how much is used and how much is free. Now let's discuss swappiness. Swappiness is a kernel parameter that controls how aggressively the system uses swap space. You can view the current swappiness value by typing cat/proc/sys/vm/swappiness. Lower swappiness values such as 10 to 20 reduce swap usage, which can improve performance on systems with sufficient random access memory. Now let's see about managing swap space. Adjusting the swappiness can be done temporarily by typing sudo sysctlvm.swappiness equals 20, or permanently by editing the /etc/sysctl conf file. To create a swap file, first, create a 2 GB swap file with sudo fallocate-l2G/swap file. Then set the correct permissions with sudo chmod 600/swap file, format it as swap with sudo mxswap/swap file, and enable it with sudo swapin/swap file. For systems experiencing high memory pressure, adding swap space can help prevent out-of-memory errors. Let's explore some memory optimization techniques. We can limit process memory usage using ulimit. By typing ulimit-m10240000, you can set the maximum resident set size for the current shell in kilobytes. Similarly, ulimit-v20480000 sets the maximum virtual memory in kilobytes. We can also use control groups, often referred to as groups, to limit memory usage. First, create a memory-limited control group with sudo create-g memory:limited. Then set a memory limit, such as 500 megabytes, using sudo set-our memory.limit_bytes equals 500 M limited. Finally, run a process within this control group with sudo gexec-g memory:limited command. Control groups provide more fine-grained control over resource limits compared to ulimit. Another technique is clearing memory caches. It is important to know that this requires root privileges. Free the page cache only by typing sudo sh-c echo1 greater than /proc/sys/vm/drop_caches . You can free directory entries and inodes, which are data structures that describe files and directories, by typing sudo sh-c echo2 greater than /proc/sys/vm/drop_caches . To free all caches, use sudo sh-c echo3 greater than /proc/sys/vm/drop_caches . Before dropping caches, it is recommended to synchronize the file system by typing sudo sync && sudo sh-c echo3 greater than /proc/sys/vm/drop_caches . Only drop caches when necessary because caching improves overall system performance. Let's summarize the best practices for memory management in Linux. First, regularly monitor memory usage with tools like free, top, and vmstat. This will help you identify potential issues before they become critical. Set an appropriate swappiness value based on your system's workload. Lower values are generally better for systems with sufficient random access memory. Use control groups to limit the memory usage of critical services. This prevents one service from consuming all available memory and affecting others. Identify and fix memory leaks in your applications. Memory leaks can cause applications to gradually consume more and more memory over time, leading to performance issues. Configure out-of-memory killer priorities for essential services. This ensures that less critical processes are terminated first when memory runs low. Implement monitoring alerts for memory thresholds. This allows you to receive notifications when memory usage reaches a certain level, giving you time to take action before problems arise. By following these best practices, you can proactively manage memory and prevent system instability and performance issues. Here are some additional monitoring tools which include Glances, a cross-platform monitoring tool with a web interface. Top is an interactive process viewer with detailed memory information. Nagios and Zabbix are enterprise-level monitoring solutions with alerting capabilities. Prometheus is a time series monitoring tool for collecting and analyzing metrics. Valgrind is a memory debugging and leak detection tool. Grafana is used for visualizing memory metrics. Choose the tools that best fit your specific monitoring needs and environment. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.